All right, so this lesson is the final one in Chapter 4. And keep in mind, all aspects of Chapter 4 are all about the same idea, which is how to solve a quadratic equation. And essentially, this is the fourth way of looking at how we can solve the quadratic equation. So solving it graphically, by factoring, by completing the square, and now the quadratic formula. And much like completing the square, the quadratic formula can be used to solve any quadratic equation, but also much like completing the square, it's not always the best approach. With all these things combined, you can always come up with a sensible approach that is, it should never have to take that long if you choose, again, if you're flexible in how you want to approach these things. But in general, to understand the quadratic formula, we first need to think about a quadratic expression in standard form, in which you have a representing the coefficient of x squared, b representing the coefficient of x, and c representing the constant term. And any quadratic equation can be written in this form if you bring everything to one side and make it equal 0. Well, any quadratic equation in this form, the solutions to x are always the same as this formula see here, which is one of the more famous formulas in mathematics at this level, in which a, b, and c, which you see here, all represent the coefficients we saw above. Now, where this formula comes from, it's actually not that difficult to get to. It comes back from completing the square. Essentially, we're generalizing completing the square. It's usually something I like to perform as a group problem, but if you there's countless videos, I'm sure, where you could see where it comes from. But in the end, this is just essentially the process of completing the square all kind of synthesized into a formula. And sometimes it's way more work than it has to be to using this. That said, let's look at an example. Okay, this would be a poor, this equation here would be a poor example to try to solve by completing the square. And that's because the first thing I would do is take out a factor of 2 from these two terms. I'd right away have 7/2, and then I have to half that and square that and do all this work. And so at this point, if I have a choice, this is a great candidate for the quadratic formula. Although really the first thing we should do is check if we can factor it. Are the two numbers that multiply to 2 and add to 7? Nope. And so now let's use the quadratic formula. So my a coefficient is 2, my b coefficient is 7, my c coefficient is 1. And so x will equal, as long as this equation equals 0, this formula see here is always correct. X will equal minus 7 plus or minus the square root of b squared, so 7 squared, minus 4 times a, or 2, times c, or 1. All of this is divided by 2 times 2 again. So I'll do my standard highlighting thing. All right, and so now I just want to simplify this. So for example, first thing I want to do, and where most mistakes are made, is actually with what is underneath the radical there. So what's underneath the radical here we call the discriminant. It's this value we get right here. And that's where most of the mistakes are made. 7 squared minus 4 times 2 times 1, or 49 minus 8. So in this case, it's pretty straightforward. It's 41. 41 we call the discriminant of the quadratic formula. But right now, that name doesn't really matter too much. The key is it got 41. And 41 is not a perfect square. I will say if you had a perfect square right here, let's say we got 49, that means we actually could have factored this. Either way, at this point, we're actually done. We should check to see if there's a perfect square we can factor out of the 41. Because sometimes, for example, like root 12, you can write as root 4 root 3, or 2 root 3. If you can do that, quite often we can simplify this expression down, but 41 doesn't have any perfect square factors. And so we're done. This is the exact answer. The exact solutions. However, as we saw with completing the square last day, you can find decimal approximations. It's by going to your calculator, typing in 7 plus the square root of 41, all divided by 4. Or negative 7 minus the square root of 41, all divided by 4. If you do that, you should get about negative 0.15 and about negative 3.35. But again, these are great answers, but they are approximations. And if you were to solve this question graphically, which if you had a device handy would be extremely fast, just graph the left-hand side, see where it crosses the x axis, you would get those decimal approximations. All right, so there's a quadratic formula. Now, please don't fall into the trap and think, well, if this always works, I should always use it. No. In fact, the next example is a great example of when we should not use the quadratic formula. That's it. I am going to use it here. It does always work, but eventually we'll see, that was actually not the most appropriate choice. That's it. My A value is 3, my B value is 5, my C value is -2. Again, it equals 0, and that quadratic formula is only correct if it equals 0. So again, I'll write the quadratic formula down here in general. Minus b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, minus 5 plus or minus the square root of 5 squared minus 4 times 3 times -2. All divided by 2 times 3. OK, so -5 plus or minus the square root. This part here is the discriminant, we call it. So 5 squared minus 4 times 3 times -2. A lot of negatives going on there. That's where a lot of mistakes happen. This is going to be the same as 25 minus 4 times 3 times -2. It's actually the same as 25 plus something. OK, because again, you're multiplying by a negative and you're subtracting a negative. If that made any sense, what I just said. But in the end, all of that there is 49. Over 6. So this is where actually I know I could have factored this, because I had, this is a perfect square. Which is great, but I guarantee this would have been significantly this would have been significantly faster if I factored it. Because I'm actually several steps away from being done. Because at this point, the square root of 49 I should write as just 7. So -5 plus or minus 7 over 6. I definitely shouldn't leave it like this, because what does this mean? This means two things. This means -5 plus 7 all divided by 6, or it means -5 minus 7 all divided by 6. And let's look at each of these. -5 plus 7 is +2 over 6, which is 1/3. There's one of my answers. And -5 take away 7 is -12 over 6, which is -2. So those are my two solutions. X equals 1/3, x equals -2. So in the end, this was a fair amount of work that, again, if I just factored this, once I had this factored, I could just see my solutions. It would have been considerably faster to factor this. And again, your job is not just to get answers correct. Your job is to show that you understand multiple approaches to solving a quadratic equation. So in the end, while this was not terrible, solving this by factoring would have been considerably faster. OK, so in general, though, I keep talking about the discriminant, that part under the radical. The discriminant, that number there, determines the nature of the roots, how many solutions there are. And so again, this b squared minus 4ac is the discriminant. And you will have no solutions if the discriminant is less than 0. If b squared minus 4ac is a negative number, then that means either you made a mistake or there's no solutions, which means that visually you have a quadratic function like this, where it just never crosses the x-axis. It never equals 0. If you have the discriminant equaling exactly 0, if b squared minus 4ac equals exactly 0, that means there's only one solution, because you get plus or minus 0, which is plus or minus nothing, which means there's no plus or minus. It's just one answer. And visually, that's when you have a parabola that has a vertex right on the x-axis. So there's one solution only. And as you would most likely expect, the majority of the time we'll get the discriminant b squared minus 4ac to be just some positive number. And any times that happens, you have two solutions. Visually, maybe you have something like this. A solution here and a solution here. And that is, again, what we usually expect. But again, these are the three possibilities, and we've seen this idea before. And again, you can tell that quite quickly from when you start working out the quadratic formula. So with that said, as long as we have our previous lessons understood, this is just another tool. And it's essentially the first thing I would always do is if you're trying to solve something algebraically, first check if you can factor it. And most often you can. And if you can factor it, that is definitely going to be the fastest. Then, if you think you can't factor it, sometimes completing the square is really, really quick, like we saw last day. But also, like we saw last time, sometimes completing the square is really cumbersome. And so with all these things in mind, you should always have several options. So the final problem is, again, a sort of applied problem involving trajectory, or actually in this case involving how height changes over time for a flare being fired. Again, some sort of basics of physics here. But as it says, a flare is fired directly upwards with an initial velocity of 40 meters per second. The height can be modeled using the function h of t equals negative 4.9 t squared plus 40t. Most importantly, that's what you see graphed in red here. This is h of t, or negative 4.9 t squared plus 40t. And you got this convenient little graph made in Desmos, all labeled, all quite nice. So the question is, find the time it takes for the flare to reach the ground, which basically is this point right here. How long does it take for the flare to hit the ground? OK, so that's the first part. I think there's a second part of the question. Yeah, how can you find the maximum height of the flare? We'll get there in good time. So first, how long does it take to hit the ground, according to this model? Well, the ground is when the height is 0, which means we want to make the height of our function equal to 0, which means we want to make our output equal to 0. So that's a lovely number. We write 0 equals negative 4.9 t squared plus 40t. And then we solve for t. Now at this point, we could use the quadratic formula. If we did, our a value would be negative 4.9, our b value would be 40, and our c value would be 0. However, I can actually factor this, which will be less work. How can I factor this? Well, if I look at the right-hand side, the first thing we should always check when factoring is a common factor. And there is a common factor of t, which I can take out here. So if I take out a factor of t, what am I left with? I'm left with negative 4.9t plus 40. Or if you want, maybe I like that better, I'll take out a factor of negative t. This becomes a positive, this becomes a negative. I kind of like that better. That said, I can now inspect my factors. I can see one of my solutions is 0. When t is 0, this flare is on the ground. But I knew that already by looking at my graph. However, it does mean something. I just didn't need this equation to tell me that. What I needed the equation for is for here. When this equals 0, that'll be my solution I actually want. And so when 4.9t minus 40 equals 0, I'll have my other solution. Or when 4.9t equals 40, or divide both sides by 4.9, you get up t equaling about 8.16 seconds. So that there is how long it takes for this flare to reach the ground, about 8.16 seconds. And again, if we use the quadratic formula, it would not be this quick. Again, the quadratic formula, you do not want to use it by default every single time. Not at all. It's important, but it's not that important. That said, the last part of this question is how could you use that value we had, about 8.16 seconds, to find the maximum height of the flare? And what's that height? So I now know, if I'm going to clean up my graph a bit here, I now know that this is about 8.16 seconds. I want to find the height from here to here. How can I do that? Well, this is a parabola. This is a quadratic function, and parabolas are always symmetrical about the vertex. And I know that's at 0, and I know I have another x-intercept at 8.16. So I know the vertex must be halfway between 0 and 8.16, which means I know the vertex must be at about 4.08 seconds, which means, according to our model, just after 4 seconds after firing off the flare, it reaches its maximum height. So that's my x-coordinate. That's my time. So how can I find the height now? Well, I have an equation that tells me how height and time are related. I can take this 4.08 and put it back into the original equation I gave you. There and there. And that will tell me the height. And so if I want to find the maximum height of this, I just need to go to my calculator and type in negative 4.9 times 4.08 squared plus 40 times 4.08, replacing time with 4.08. And that will tell me the height at that instant. And if I type that in, I get about 81.6 meters. So I now know this is about 81.6 meters. That's the maximum height. There's other approaches. I could have completed this square, which would have been way more work to find that maximum height. But again, it's always nice to remember the basics. And that is quadratic functions are symmetrical. And so if I know these two x-intercepts, which I knew fairly quickly, I know the vertex had to be halfway between them. which means it had to be halfway between 0 and 1.86. And things came together quite nicely there. And there we go. Hugely important chapter done. And I'm going to stop here.